Hello, so let's continue with our periodical lectures here at ICMAB, trying to open our mind beyond pure material science. So it's a pleasure for me to introduce today Reguant. She did the PhD in economics at the MIT, yes? And then she also worked in Stanford and the Toulouse School of Economics, and also at the Northwestern University, that you still, I think, have some kind of relationship with them, yeah? She's right now an ICREA and in a neighbor building at the IAE-CSIC here. And she's going to talk about this smart rationing, designing electricity blackout policies for extreme events. So please go ahead.
Perfect. Thank you. Thank you, Albert, for welcoming me here. I'm very excited to be presenting this work, which is about blackouts. And as I was mentioning informally before the start of the talk, I was doing this work before the Spanish blackout. And you will see that the type of blackouts that I study are different than the one we had in Spain, okay? So I'm sorry to disappoint anyone who was looking for answers on what happened the day of the blackout. So in this audience, let me fix this 1 second. So in this audience, probably I don't need to motivate too much that we need to decarbonize our economy broadly, and that the electricity sector is where we have seen most efforts. But we see signs of increasing pressures on the electricity sector. One is that we have already done quite a bit. And now renewables intermittency, the fact that we don't choose when they produce, is becoming more important than maybe when we had a little bit of renewables in the system. That would be the case where we have too much solar, but it's in the middle of the day, and then at night you don't have solar. So these limits are becoming more visible as we approach more decarbonized systems. But the other thing that we worry about is two additional things that are related. One is the increase of extreme events because of climate change. And this puts pressures both on the supply and the demand side. On the supply side, extreme weather can really hamper power plants and can hamper our ability to harness the transmission grid, for example. And on the demand side, under an extreme event, typically electricity demand will be very high, either because it's very hot or because it's very cold, typically. A tornado is a bit different, but think about extreme hot, extreme wind. A tornado would probably damage much more the supply side, and the demand might be less affected. And then on top of that, we're trying to feed in more electricity into this system because we're trying to decarbonize other parts of the system. It does not help that now we are also trying to add artificial intelligence demand into the system. So these are all growing pressures that we have. What I study is situations in which you need to do rationing. These are situations that economists don't like to study because it means that the supply and the demand failed to meet. Basically, it's situations where the demand is so high that the supply cannot achieve an equilibrium, and you have to start rationing. This is what's commonly known as a plant blackout or rolling blackout, or sometimes it's called load shedding. It's the idea that we reduce demand by preventing demand from existing. We black it out to ensure that we still have enough supply to provide the remaining demand that's in the system. Now, I had this idea for this project a very long time ago when California was undergoing wildfires, and they were having blackouts, planned blackouts to deal with fire risk. And it was kind of a dormant project until the energy crisis, when in Europe there was this sense that maybe supply and demand will not be able to meet. At the end, it didn't happen, but there was this concern that there wouldn't be enough natural gas if the winter was particularly cold. And that even though they reduced demand from industrial sectors and households quite a bit, there was this growing concern that maybe we don't have enough supply to meet demand. So this is the type of blackouts that I will talk about. Here in Europe are more of a concept than an actual fact, but they are more likely to happen in the future for the reasons that I was giving you. And in the United States, these blackouts are not very common, but quite common considering how unlikely they used to be. In Texas, every summer, they have situations where there is not enough supply for cooling. And there was also the case of a very cold winter in which they had a 1-week blackout. So during 1 week, there was not enough supply to provide electricity in the state. And that, again, is very, very uncommon for for a state like Texas or a country like the United States. That said, blackouts are very common in developing countries. In developing countries, sometimes it's because there is not enough supply to meet demand, or sometimes it's because that supply would be too costly for the government, and electricity is often subsidized, so oftentimes there are these type of blackouts to prevent demand from being too big. So again, they are relatively unlikely here, very unlikely in Europe. We're kind of lucky that we have a good grid despite the Spanish blackout. But they are more likely to happen in the future, again, probably in Spain in a very hot day or in a very cold day. These are examples from Texas, which, as opposed to Spain, has a very flimsy grid, but similar to the Iberian Peninsula, is disconnected from the rest of the US. So it's a very vulnerable state. And as I mentioned, they have had both summer and winter blackouts that are due to insufficient supply combined with extreme weather. In summer, it happens more or less every summer. And in winter, it's very rare, but there was this case of 1 week blackouts, and more than 100 people died from that event, because being without electricity in a moment of extreme need can be quite dangerous. As I was mentioning, in other countries, this is very common. In South Africa, they have been undergoing rolling blackouts. I always say they call it Monday and Tuesday. Literally, they have a schedule, and they know it is going to happen every single day. And another example where I'm starting to do some work with a utility there, that's why I highlighted here. In Vietnam, they also have rolling blackouts due to extreme hot weather. Although they are relatively functional, but they still sometimes cannot avoid this rationing. So the goal of this paper is to think about what can we do with the existing infrastructure. So yes. So here it is the type of blackouts that I'm studying are national blackouts, in the sense that the country doesn't have enough supply to meet demand. But it doesn't mean that it's like Spain, where everything goes dark. It's a planned blackout where you black out certain parts of the country, a neighborhood, several neighborhoods, but you do it in a planned way. So it's not like in Spain where you got zero power. Yes, you just reduce demand artificially to make sure that you can sufficiently produce electricity. Yes. So ways people deal with blackouts in Texas, where they are relatively common now, people get batteries, solar panels, diesel generators at home, and they privately provide for a solution for themselves. So if there is a blackout, they will themselves still have electricity. Other places, they are putting microgrids in schools or public district centers, where they know that if there is a blackout, the school at least will have power and backup power in the town. What I will be talking about is solutions that don't require capital investments. I will be trying to think, given with what we have now, understanding that we will have more batteries and we will have more backup power in the future, but given what we have now, how can we do blackouts better, okay? And how can we do them in a way that they do not harm low-income households? Because all of these solutions tend to favor high-income households. Definitely putting solar panels and a battery, you need to be a high-income household, but also the example about the district microgrids, this example where they have been more far ahead is Santa Barbara, which is one of the top 10 postal codes with the most income in the United States. So all these fancy solutions tend to happen where people have more money. What I will be thinking about is still Armageddon kind of situation. We still need to have a blackout. We don't have enough batteries. So how can we do these blackouts in the best way possible, exploiting smart meters? And that's the goal of the project. Yes?
So blackouts would be help in the sense that if I know tomorrow there's going to be a blackout, all consumption today of electricity might go up, even if tomorrow going. So are they really useful in reducing demand?
Yes, they do reduce demand, even though people can substitute a little bit. But there are many base consumption that really will be reduced by a blackout. Here, I assume that my solution on a blackout would have similar implications. The solution I propose would lead to a little bit less substitution across hours, but I kind of ignore it here, yes. But they definitely will reduce demand a lot, yes. Yeah, even if you can substitute a little bit, yes. And from Texas, the blackouts were rolling blackouts. So some neighborhoods would get no power for 5 hours, but we were in a situation where the heating would have been on 100% every single hour. So there's no concept of substitution when you really need power nonstop. Yes. Great. So what's the solution that we examine in this paper? It's the idea of using power limits in smart meters as an alternative to blackouts. What are power limits? In this room, potencia contratada. You know, your contracted power in your smart meter. In the US, it's very hard to explain that they can limit your consumption at the home. But here, is there anyone who's not familiar with a potencia contratada? It's this idea that if you plug too many things in the house, the lights go off and they tell you, you have too many things connected in the house, so you need to step down. So why is this an opportunity that we had not harnessed? Well, traditionally, the potencia contratada, these power limits, were a fuse in your smart meter, not non-smart meter, in your traditional meter. And if you paid more money, they would put a bigger fuse. And if you paid little money, they would put a shorter fuse. But if you wanted to change it dynamically, there would have to be a person going over each meter and changing the fuse. Oh, bad day, short fuse. Oh, good day, long fuse. Nowadays, we can do that digitally. And the idea is to exploit this to dynamically set limits in the homes in moments of extreme need, with the idea that by doing so, you will not have to do any actual blackout. People will still have power, but it could be that they have much less power than they would otherwise. So that's kind of what we explore in the paper. And we do so in 2 ways, theoretically and with simulations using very detailed smart meter data from a utility in Spain. On the theoretical part, this is the part that we were most surprised about and what I will try to tell to you in the presentation. So when we started thinking about these power limits, again, originally a long time ago in the context of California, it seemed to us this has to be better, at least on average, because you are giving people some power rather than leaving them stranded without power. But our intuition was that, yes, we will give people some power, but then we will need way more many people to help, right? Because we're giving them something. So what we found out in our theoretical investigations and empirical investigations is that we can use power limits to simulate a blackout, but still giving power to people, which is what was our goal. Can we do something equivalent to a blackout that's a bit less aggressive? But our surprise is that we actually end up bothering fewer people than under a normal blackout. And this was really very surprising to us, and it's not very intuitive. So I'll try to convey the intuition. Basically, if you had one person that's the same everywhere in the world, so we are all the same, this would not be true. When you have a power limit, you are being more generous, you need more people to contribute. But in reality, people are not the same. People are different. So what we're finding in the theory and the data is that when you put a power limit, some people don't even notice because they are low consumers. But some people notice a lot. And if those that notice a lot are big enough, you can actually end up with a situation where most consumers don't notice that there is a blackout, but the very high consumers are the ones that actually making the effort. This is without explicit targeting. We are not saying, let's go after the high consumers, but we are kind of going after the high consumers. So in the second part of the paper, we ask, is this a good or a bad thing to go after the high consumers? Okay, so I'll get to that later. Do you have any questions on the motivation? Yes? Yes. Oh, very good question. So industrial consumers, they have a special programs for interruptible contracts, and they do call them up when the situation is very bad. This paper is kind of Armageddon Day when you have run out of buttons and you want to resort to households. But politically in Europe, that's the last button kind of that you would press. In developing countries, by the way, it's very different. In developing countries, households, it's typically the first button that you press, and you go only later after industrial use, but here it's the last button that you would want to press. Yes. Yeah.
We're talking about power control. We are thinking about some kind of automatic system that will put limits in the power depending on, I understand. General limits for everybody.
Yes. So, well, automatically, it would be very similar to a rolling blackout. In a rolling blackout, they tell you tomorrow there is a curtailment and this neighborhood will not get power from 3 to 6. Here it would be tomorrow there is a major need and your district will get reduced power from 3 to 6. So it's not quite automatic. The distribution company needs to send a message to the smart meter that your potencia contratada during those hours is not what you paid for, is something lower. Yes. So that's the idea, that you just change the potencia contratada. This is technically feasible. They already do it for electric vehicle users. You can have different potencia contratada at night or during the day. The most typical use case is an electric vehicle, that you basically decide which hours you want to charge at high speed. And then every day they change it from night to day, yes. But it wouldn't be automatic as the automatic response from a power plant. No, it would be sending a message that the smart meter from 3 to 6 cannot use as much electricity as in normal times. Yes. Typically cars in Spain are not used as a battery, but in the US they use them as battery. What comes as a, I would have to check, but I think it would be the, yeah, but I would have to check with how the, my sense is that it would be on the net, With a solar panel, it would be on the net. But with the car, I would have to check, I think it's the same, because all of this happens behind the meter. So if your house is consuming less because you are creating solar or you are using a battery, you would not be affected. Yes, you would not be affected. Yes. Yeah, that it's an interesting question. So in South Africa, they are doing a pilot, and basically they have bought consumers into the program by excluding them from some mild blackouts, and then as a compensation, they have the smart meter. The case I had in mind when I was writing the paper is Spain, and in Spain, every single person has a smart meter. It's true that it could lead to people fudging, but we have to remember in Spain, these are very unlikely events. So I don't think it's worth it for a person to tinker with a smart meter, given how unlikely these events are. In South Africa, maybe people would have more of an incentive to go around it because smart meters with power limits are not universal. So they kind of bought people into the program. Yes, but it's a good question. Yes. Great. So when are these power limits that I have in mind useful? They are not useful for the blackout we had in Spain. It was kind of unexpected, and it was because we had too much power, not too little. They were also not very useful in the case of California. So we talked to the distribution companies there and the transmission operators. And basically, when there is wildfire risk, the topology of the network matters a lot. So sometimes they really wanted to shut down an entire neighborhood. They didn't want the neighborhood to be less congested or less tensed. They just wanted it to get out. So it depends on the type of problem, but it's most useful for situations like the ones I mentioned, the European crisis, the Texas blackouts, weather-related Texas blackouts, and California also had some weather-related near blackouts where they had to really rile up the population to reduce power. Yeah, so it's again a last resort solution. Will they be useful? So in Spain and France, it's where we are most prepared to use them, but it's where these things are not very likely. But we already have smart meters, 99% of the population with this capability. In France, actually, during the energy crisis, they did a pilot on this. Me and other people were bugging them to try to explore this, and they did put it into law. So it's legal to do this in France. And they did a pilot that has a lot of validity. It was one town, one day, 2 hours. But the pilot saved 40% of energy. You know, what can we learn from this? I'm not very sure. It was a rural town, but you know, there's that. In other places like South Africa, I haven't been able to talk to them. How well is it going? But they did try it out in several neighborhoods in the order of 60,000 smart meters. And in the US, it depends, because limits to people are not something that they process too well. So many smart meters are perfectly smart, but they don't have this capability. It wouldn't make the smart meter much expensive, but it's just not something that they thought would be ever useful. So some states that could really benefit from this, they might need newer smart meters or different smart meters. Okay, so let me tell you about the framework. The framework is very simple. We will be thinking about people who consume X. I put the price in there in the first equation because I'm an economist, but I will think that the price is as high as it could be. And we're still in a situation where demand is too high and we need to curtail it. We need to reduce demand. And we will be thinking about the rationing mechanisms that basically limit the consumption of a household to a limit kappa that's potentially below their consumption. In a blackout, kappa is 0, so you get nothing. But we will consider situations where we give something to households that's a bit higher than 0. Now, traditional rolling blackouts, I already mentioned this, kappa is equal to 0. Some households get nothing, and the rest go about their business. The going about their business, I put it as kappa upper bar. So the highest kappa you can get, no impact. Now, what's the problem with a rolling blackout? In economics, we think about welfare, and here I'm expressing welfare as the combination of 2 types of households. With probability alpha, you get 0, and with probability 1 minus alpha, you don't notice. Now, our worry as economists is that having 0 is very, very costly. Particularly if it's an extreme event, you might want to ensure that people have some electricity. In the case of rolling blackouts, the problem is also that when you have a rolling blackout, the streets don't have light. So it also becomes dangerous for businesses and whatnot. So we'll be trying to go away from having alpha people getting 0 to something else, okay? So what we will do? In theory, the smart meter rule could be different for everyone. But I'm gonna just not do this and do something very simple. Everyone gets the same limit, okay? That's what I will be focusing on. So rather than getting a limit of 0, which was the blackout, we will select an amount of people beta. So the probability of being selected is now beta. And now we give them something that's between the upper limit and 0. So in between. The utility function is very similar to before, but now notice that the ones that are kind of left behind don't get 0. They get something a bit more. They get selected with probability beta. And the 1 minus beta, other fraction of people, they can go about their business and they just don't participate in the scheme. Now, we will be trying to think about equivalent policies where we choose beta and kappa so that we have a blackout of size alpha. So what's that frontier? What limit can I give to people and how many do I need to select so that I reduce demand equally to a blackout of size alpha? In the simulations, alpha will be 5%. So what would we need if we want to reduce demand by 5%? Now, intuitively, this is what is most intuitive. If you give something to people, you need more people to participate in the scheme. So beta will have to be necessarily higher than alpha. And this is why my intuition is that I would be bothering more and more people with this scheme. Now, why doesn't it quite go through? Well, only those that are above the limit actually notice that there is a blackout. So in this scheme, we will have many people that are selected. They get a limit in their smart meter, but it doesn't affect them because they were going to be below the limit anyway. And this is what we defined bothering people. So are they effectively rationed or are they just selected but they don't notice? So a key component to determine how many people notice is to think about the conditional expectation of my consumption if I'm actually above the limit. So this would be the expectation of consumption for those that actually notice that there is a blackout. And what we show in the paper is that if the distribution of consumption is heavy-tailed, and by this I mean heavier-tailed than an exponential distribution, these high users contribute more than what you are giving to the rest, and therefore you get that fewer people get affected by the blackout. It's just different people, okay? But that's the main mathematical result that we have in the paper. Another way of putting this is that this equation, the probability of being selected, beta, and whether you are affected is the second component. This probability is equal to alpha for an exponential distribution, and anything farther-tailed than an exponential, people who notice there is a blackout are less than under a normal blackout. Yes?
Sorry, it's a stupid question, but I want to have a good ones. But if everyone consumed less than the rational, would you actually say that? No, you would have zero impact. Importantly, here we are looking at alpha equivalent blackout policies. So for a policy that manages to achieve a reduction alpha, but yeah, if you give a very generous limit, you will get a blackout of alpha equal to 0, no effect. Yes, this is related to my next slide, which is where your mind, I think, is going at. Limits to power limits. This sounds too good to be true, no? So what's the trick? Well, if you do this generous policy, you cannot achieve 100% blackout, certainly. You would not be able to do it. So what we defined in the paper is what's the maximum blackout size you can achieve under this more generous policy. The thing is that a blackout of 5% is already a massive blackout. A blackout of 10 or 15% would be a ridiculously sized blackout. And what we find is that for many of these limits, these type of blackouts are within the feasible space. But if you wanted to achieve a 90% blackout, it might well be better to just do a blackout and that's it. Yes, because it's not very feasible. Yes. Now, are power limits a good thing? I think in the objective sense of fewer people notice and everyone has power, that's already two very good things. It is better, this policy. However, some households are more impacted than before, and some households are less impacted than before. So in the paper, we ask, theoretically, is there a case that everyone is better off? The ones below the limit, absolutely, because before they had some blackouts and now they never notice that there is a blackout. The ones above the limit, we just try to make the point that it depends. Sure enough, they are impacted more, but when they are impacted, they still can consume kappa. So if their consumption is not too far from kappa, they might prefer that to having some days with zero consumption. On the other hand, if you're very far from the limit, you prefer to be bothered very, very little, even if it's dramatic when it happens. Okay? But that's kind of the points that we do theoretically. I put here some math because this is ICMAB, but I'm not going to go over these equations. We basically define what is this frontier of being better off or not better off for the relevant households, and we just put some utility functions in there, but I'll skip it for the sake of time so that we can go to the empirics. Now, for the empirics, we will be thinking about, is this good or bad, by trying to link it to whether people need that power and why. So we will try to, it's a bit simplistic. Economists find it a bit too normative, okay? By normative, what we mean is that you're being a bit prescriptive, okay? But we try to separate need or consumption of electricity along two dimensions. One is you have more money and you can consume more. And the other one, you need it for heating and cooling. And we separate these two different sets of needs. In my opinion, and under a standard economics, if you need it because you have a particular need, it is socially more valuable. If you are already consuming a lot and you just want a little bit more, maybe it's less important. So we will try to see whether income is a big driver or further needs of electricity, in particular heating and cooling, are the biggest driver, okay? So this is a typical assumption we make as economists, is that higher income consume more. but it's true on average, and in practice, there's lots of evidence from many countries that there is a lot of heterogeneity. For example, there are some papers that find that unemployed people consume more because they are at home. There are some papers that find that low income consume more because there's way many people at the house. Or lower people consume more because their houses are very crappy. And sure enough, you're cold, but you're still wasting a ton of energy trying to make it a bit warm. Okay? So it's a bit of an empirical question. For the empirics, we have data from many smart meters. It's about 4 million, but many of them seem too high to be a household. Some of them are always shut off. So we clean it up. Some of them we have a very small sample. So we look for the households where we have the complete sample. We clean it up a little bit for empty houses or houses that look too big to be a household, and basically end up with about 1 million, 0.3 household data. We link it to the postal code, which we observe. And for the postal code, we obtain the income distribution of the zip code. So we will know, are you in a high income zip code or not? This is the location, so it's not Endesa, bottom line. Endesa is the one serving Barcelona. But importantly, it's a distribution company. So we have everyone in that area. We observe everyone. It's not a commercial company. The distribution, very small, honestly, coming from the US. I'm Catalan, but coming from the US, this is shocking how little people consume in Spain. And fat-tailed, even though it's hard to see here. Okay, but this is fatter-tailed than an exponential distribution. The simulations we do are very mechanical. Yes? This would be hourly data plotted. Yes. Hourly. So 1.3 million times a year and a half times 24. Yes. A lot of data into this graph, I guess, but every observation is 1 hour person or 1 hour household. Yes. So the simulations we do are very simple. Every household, we have their hourly consumption for a year and a half. So for every hour, we will be checking, are they above or below the limit? And we will be creating alternative consumption if we just cap it. So for uniform power limit, we just say, are you consuming above or below the limit? And we make the assumption that if we set them a limit, they will be able to stay there. In practice, they reduce consumption much more, but it's kind of being conservative on what the blackout would do. And then we consider different limits, 500 watts, 750, 1 kilowatt, and 1 kilowatt and a half. And we will be finding beta, the probability of selecting, so that the combination of kappa and beta create a 5% blackout. And we will be doing that for every single hour in our sample. So for every single hour, we will be creating mini blackouts that reduce demand by 5%. We also consider something a bit more controversial, but that economists sometimes like more. It's not going to have very good properties, okay? But we consider, what if you are rationed depending on how much you pay? So in our data, we also observe how much people contract for their limit. So la potencia contratada. So we ask, what would happen if we give people half of their contracted power or 20% of their contracted power? In particular, we do 7%, 15%, 25%, and 35%. So now, in this example, the limit is different for every person depending on their contracted power, okay? Now, what do we find in these simulations, the mechanical simulation? So this is a blackout. This is a blackout, this column is a dummy, okay? This means one, we select one person and we black them out completely, and therefore we get potentially 100% blackout, and the people that get a blackout are 100% affected. Let's pick one, let's say the 500 watts. So if we do a 500 watt kilowatt, what we find is that we need to select about 2 people, close to 3 people. So for every person that had a blackout, now we need 3 to be selected into the scheme. But only half of those 3 will actually notice that there is a blackout. Why? Because 2.5 of those people are below 500 watts, so they don't notice. In terms of max percentage safe, this is a more generous scheme, so the most we can achieve is about a 35% blackout. We cannot go higher than a 35% blackout, but this is a really very massive blackout. And then the final thing we do is to look at daily blackouts. So we try to think, what if this is a rolling blackout and you get the limit during the entire day? Sure enough, maybe I don't hit the limit at 3 a.m. in the morning, but I might hit the limit at, I don't know, 5 p.m. So this is the teal bar. So out of these 3 people or 2.5 people that I was mentioning, about 2 of them will at some point in the day notice that there is a blackout. This means that 1 hour or 2, they will hit the limit. But you can see here the percent, it's really much more a small percentage. So for people with a blackout, 100% of the hours of the day, they hit the limit because the limit is 0. Whereas with a half a kilowatt limit, it's about 20% of hours where households hit the limit. The rest of the hours, they can operate their home at a normal use. So it's potentially, again, much more generous. So going at, is this good or bad? We correlate these impacts, that you see here in the aggregate, we correlate them with income and with heating use. To do that, we leverage on previous work where we used machine learning tools. We used machine learning tools in this other paper to basically unveil, using the smart meter data, do people have heating, do people have cooling in this house? And using the zip code level data for income, what's the expected income of these people, okay? The first part is very engineering driven. It correlates temperature during a day to your electricity use. If it's very cold and you suddenly use a lot of electricity, you conclude that people have electric heaters. Or if it's very hot and people use a lot of electricity, you conclude that they have cooling. So it's relatively more mechanical. Let me tell you more about how we infer income. So the naive approach would be to use our census data to take the zip code income and assign it to each household. So if I'm Mar and I'm from Suria, I will assign myself the income distribution of Suria. Now, Suria is a bit like Granollers in a tiny version, but it's very heterogeneous. So in reality, there's people who have quite high income and people who have very low income. And you miss a lot by just thinking that everyone in Suria is the same. So what we do is basically come up with machine learning methods to try to improve the guess that we have on income. How do we do that? So we'll be thinking about households as being of different types. The easiest is to think about cars. So if Suria, everyone is different, and somebody is driving a Porsche, and somebody is driving a Seat Panda, if you had to get a very wild guess, who has the higher income? The person with a Porsche, okay? So we will be doing something similar with electricity. So high-income people maybe consume more, or maybe they consume at different times of the day, or maybe they consume more on the weekends or less, I don't know. But we will be trying to infer, based on how much people consume, what's their income. Importantly, keep in mind we also observe the potencia contratada. And the potencia contratada is very correlated with income. High-income people don't want to deal with it. They put a high limit so that you never find out what potencia contratada is. Low-income people actually understand it's a big part of their bill and try to game it more. So we will be using potencia contratada as one of the explanatory variables of whether you're driving, it's our Porsche version, okay? Do you have high contracted power, low contracted power? The method, I will explain it with 2 zip codes. Let's think about Suria and Manresa, which are nearby towns. And we'll be unveiling what type of people are in Suria and what type of people are in Manresa. Imagine A is low potencia contratada. Actually, imagine A is high potencia contratada and B is low potencia contratada. And imagine Suria has higher income than Manresa, for example. If we see more people with high potencia contratada and Suria has higher income, we'll conclude that people with high potencia contratada are more likely to have high income. We will not say they have high income for sure, but the estimator will tell us that they tend to be higher income. And this is how the method will work. This is a very simple version where we have to make lots of assumptions. In practice, we do a more relaxed estimator, but this is the main intuition. Now, in step 1, what we do is classify people based on their smart meter data and their potencia contratada. We'll get them into groups. This is an example of the groups we have. People that consume during the day, and at night, people that only consume at night, people that consume in the morning and the very night. So this is giving you patterns probably on their work day, on their income, also depending on the amount, okay? So we classify flexibly households. Then we bring it to the second step. The equations are a bit more complicated than the two-type estimator, but that's what we use. I really don't have time to get into the details. And then we get the results. Now, to convince you that this method is useful, and especially for the type of analysis I do with the blackouts, I will show you contracted power. So here we have contracted power, and here we have the income quintile that's predicted in the data. Imagine I use the naive zip code level data, only zip code level. You can see that contracted power is positively correlated with income, but you can barely see it. If we use our method, we unveil that contracted power is correlated with income. We use the consumer expenditure survey as a validation for our estimation. We never use this data in the process. And you can see that in the consumer expenditure survey, we have a similar pattern than the one we uncovered, where contracted power is even more correlated with income, okay? So that's to motivate the method and to say that it's very important if we want to understand the equity implications of limits based on contracted power, okay? If we use the gray line, we would find that the limits don't matter much. But if we use the black one or the teal one, which is the one that we are able to recover, it's clear that contracted power is very, very correlated with income. Going back to the outcomes, what do we find? So we create these equivalent policies to a 5% blackout. We find that uniform rationing, the same limit for everyone, is progressive. Importantly, all of these lines are below 5%. So within an income quintile, on average, for all income quintiles, people are bothered less than under a blackout. Why? Because within each income quintile, which are the different bars, there's high users that contribute more than the others. For low income, this would be the lighter color. You can see that with uniform, it's at the bottom. So people with low income are affected less by the mechanism. This is also true when we put high or low limits. Now, when we have heating or cooling, you can see that income matters much less. If you have heating or cooling, you are affected regardless of your income. And without cooling, then the effect is even more noticeable. So for people without heating or cooling, income is a big driver of whether they are affected. But if you have heating or cooling, you are affected for sure. Now we compare it to proportional rationing, and you can see that proportional rationing is very regressive. First of all, what we can see is that the low income are now at the top rather than at the bottom. So they are affected much more frequently. And importantly, this line even bends. As we are more and more generous with the limit, the low income get affected even more than the high income. Whereas under these simulations, as you make the limit more generous, all income quintiles are affected less. But if you make it proportional, and you make the proportional limit very generous, only the low income are affected. So very different consequences on who gets affected and why. So this is what I had. We have many open questions that we don't answer in this paper. So one of them is the more engineering aspect of it. When we were working with California, there was a limit on how many smart meters you can contact at a time from a telecommunications point of view. So we are trying to understand, is this a limiting factor or not? How often can you modify the limit? The other thing that we are trying to do is try to think about using power limits in normal times. So if we are able to use the price, again, under an extreme event, I don't think I would want to use the price, but imagine it's low wind day or low solar day. If we can do some contracts where people participate via power limits. What's the advantage of power limits? Well, that the limit is very, very binding. You can ensure that it will happen compared to voluntary reductions of demand, which are harder to assess. Even price reductions of demand, so putting a high price so that people reduce demand, it's much harder to predict how much people will reduce consumption. So here, the idea would be that people get a lower price of electricity in general, but some days they are willing to have a limit because, again, it's a low solar day or a low wind day. Another case example is electric vehicles, that for a lower price, you are willing to restrict the days in which you charge your electric vehicle, even if some of them are without notice. So they tell you the day before, look, tomorrow you have to be careful charging your car, you have to charge it as a slow rate rather than a fast rate, which is very easy to do for people with cars. So this, I'm starting a project with Estabanell, which is a tiny distribution company in Granollers. And we might be doing some experiments with this, but it's very early work in progress, so not yet much to show. So the summary, power limits, I think they are powerful. We had not used them before because they were fuses that you had to change in boxes, but nowadays it's a real tool to deal with a scarcity. Here, scarcity is unlikely, but in my opinion, still worth studying and implementing, even if it's unlikely. But then there is this open door for more commercial applications to these type of limits that open a whole set of different questions and a whole set of other methods that would need to be developed. Great, so that's it. Thank you.